11th lecture on wave shaping circuits, and if time permits we shall introduce the topic of natural response of circuits. As I had talked about yesterday, we were considering a differentiating circuit C and R, and if this is Vi, this is V0, then V0 is approximately equal to RC dVi dt, provided the product RC is much less than capital T, where capital T denotes the time period of Vi, the input voltage. And I said that if the input voltage is a rectangular wave like this, if this is Vi, then V0 will be the differentiated form, and if it was ideal differentiation, then the slope should have been infinity. Alright, so there should have been an impulse here, an infinitely large amplitude, zero duration, and there would have been a negative impulse at this point where the amplitude goes down. Alright. In practice what happens is, as soon as this waveform is fed here, the capacitor, which was uncharged, cannot change its charge instantaneously. So the capacitor acts as a short, and the total voltage is dropped across the resistance R, and therefore the voltage rises, the voltage across the output rises from 0 instantaneously to the value Vi. Then what happens? Then the capacitor gradually charges, so this voltage decreases. You see, by KVL, Vi should be equal to Vc plus V0. So when Vc increases due to charging of C, the voltage V0 decreases, and this is what happens. It rises to Vi, then gradually it diminishes exponentially, alright, and diminishes to approximately 0 till the voltage comes here. At this point the voltage goes in the negative direction, and therefore, I'm sorry, I've made a mistake. I wanted to take the general case of a voltage which goes positive as well as negative, general case. So my zero level, let's say, is somewhere here. This is the zero level. Then what happens is, the voltage goes up like this, it diminishes like this, then when it comes here, the voltage goes down like this, because the charge is approximately 0 here. Once again, as soon as the input voltage changes to the negative level, it goes to the negative level, then again the negative charge decays, which means that the voltage rises towards 0, remains there, then again it goes up, it comes down, and so on. It repeats. And these waveforms, which have very sharp decay, the duration of the waveform is very small, are called spikes. So what you would observe in the oscilloscope would be these spikes. There would be a spike here, a negative spike here, positive spike here, a negative spike here, and so on and so forth. Alright, this is the differentiating circuit. Now if you recall, in the differentiating circuit, the condition under which the circuit differentiates is that V0 should be much less compared to Vc. Alright, V0 should be much less compared to Vc, or the product Rc should be much less than capital T. Question is, can we obviate this constraint? Can we design a circuit in which this constraint is not needed? In other words, you see, if V0 is much less than Vc, what it means that the output voltage is a very reduced form of the input voltage, reduced replica, not replica, reduced differentiated form. Can we do something to obviate this difficulty? Well, this is offered by the op amp. If you take an op amp in which the non-inverting terminal is grounded, the capacitor is connected here, C, and the resistor is here. The resistor is in the feedback path. This is V0 and this is Vi. Suppose I consider this particular circuit in which the op amp is assumed to be ideal. Now, if the op amp is ideal, then you know this, if this is ground, this point shall be virtual ground. This point should be virtual ground, which means that the current through C would be simply C dVi dt, and the current through R should be equal to V0 by R. Agreed? And by KCL, the sum of the two currents should be equal to 0, because the op amp does not take any current, infinite input impedance. And therefore you notice that V0 is simply equal to minus RC dVi dt, and this does not involve any assumptions whatsoever. It doesn't involve any assumption about the product RC or that the output voltage is much smaller compared to Vi. No assumptions are involved. So this is a better differentiator. This is what the op amp does. It improves. You see, we use the same elements, a capacitor and a resistor, but in between we use an op amp to improve the differentiation. And this relation, if the op amp is ideal, is exact. There is no simplifying assumption involved here. This is what the op amp does. This is the op amp differentiator. In a similar manner, we can get an integrator. An integrator is a series resistance and a shunt capacitance. This is Vi, this is V0. This is the passive circuit, this is R, and this is C. And you see that V0, yes?
So in the previous case, if we increase the resistance very much, even large, so
Yeah.
then output voltage will also increase. That means it can magnify the output voltage.
Previous case means what? This case?
In this case, yes, sir.
In this case, if you make capital R very large,
Yes.
okay, CR will increase, fine.
So, sir, it may magnify the output voltage.
So what do you mean by
It will
magnification?
increase it.
You see, magnification or amplification, the term is used when the waveforms are preserved. That is, if the output waveform was of the same shape as the input wave, then the term amplification or magnification makes sense. Otherwise, if you are changing the wave shape, what is it that you compare? The two shapes are different, and therefore we don't say magnification. What I am saying is that the RC product now is arbitrary. It has no relation to the frequency or the time period of the input waveform. Alright? Okay, in this case, in the case of the RC circuit with capacitor shunted, capacitor as a shunt and a series resistor R, which is exactly the differentiating circuit with C and R interchanged, while Vi is equal to VR plus V sub C. And if V sub C, that is the capacitor voltage, is much less than VR, then Vi is equal to VR. Which is equal to, if the current in the circuit is I, it is simply equal to I times R. And therefore the current in the circuit is given by Vi divided by R. Alright? If Vc is much less compared to VR, and this shall be valid if Rc is much greater than capital T. If Rc is much greater than capital T. This we will see independently later on, but you see that the current in the circuit is determined by resistance only, and therefore the output voltage, that is V0, output voltage V0, which is the same as the voltage across the capacitor, shall be given by Q by C, that is 1 by C, and Q is integral I dt. But I is Vi by R, and therefore this is 1 by RC integral Vi dt, which means that the output voltage is proportional to the integral of the input voltage. All right. Therefore, this is an integrating circuit. The constraint is that the output voltage must be very small compared to the input voltage. Now, to take an example, if I have a square wave once again like this, then what happens is due to integration, well, physically you can see what is happening. Let's not go into the mathematics first. Physically what happens, you can see that when Vi is applied, if it is a square wave, suddenly Vi rises from 0 to a value, let's say capital V. The capacitor cannot change its charge instantaneously, so the capacitor starts from 0 charge and then gradually gets charged. All right. If sufficient time was allowed, the capacitor would have charged to the maximum of Vi. All right. When the square wave goes negative, well, the capacitor naturally charges like this. Suppose it starts from here, the capacitor charges like this. When it goes negative, the capacitor gets charged in the opposite direction, which means that it gets discharged. So it discharges like this, and once again from here when the voltage goes positive, the capacitor charges like this, and so on. Ideally this should be straight lines. If we are really integrating, then what we show as violet lines, which are curved or parabolas, not parabolas, they are exponential rises, ideally they should be straight lines. They would be approximately straight lines if the time of charging and discharging is small. Isn't that right? For an exponential curve like this, if you consider a small portion, well, it can be considered as line, as a straight line, and therefore it would be approximately an integrator if RC is far greater than T. That is, the time available for charging on and discharging is much less compared to the time constant of the RC circuit. This is the physical explanation of a passive integrating circuit. Now the relation V0 equal to 1 by RC integral Vi dt is valid if RC is much greater than T, and this restriction, exactly like the differentiating circuit, can be removed if you use an op-amp. Let us see how this is done. We have an op-amp. Once again, the inverting terminal is grounded. To the non-inverting terminal now you apply a resistor and in the feedback path you insert the capacitor C. This is V0.
So we applied to the inverting terminal.
Inverting terminal, that is correct. We apply to the inverting terminal, not to the non-inverting terminal, no. Now you notice that if this is R and this is Vi, then this current is Vi by R, and this current would be C d V0 dt. The reason being that this point is virtual ground, Vg, and therefore this current is Vi divided by R, and this current is C dV0 dt. That is, the potential difference between these 2 points is V0, and therefore the current is C dV0 dt, and the sum of the two should be equal to 0, which means that V0 would be equal to minus 1 by RC integral VI dt. Agree? And there is no assumption about the RC product here. There is no assumption, and therefore this is a much better integrating circuit as compared to the passive integrating circuit. An example now. Suppose I have a resistor R1, voltage V1, voltage V2, resistor R2, two voltages, all right, and let's say we have the op amp and the capacitor C here. What do you think the voltage would be, the output voltage? It can be obtained by superposition and can be written down by inspection. It can be written down by inspection. It would be minus 1 upon C, all right. The resistors are different, and therefore we get integral V1 upon R1 plus V2 upon R2. This will be the total current multiplied by dt. All right. We have written this down by inspection. Consider a couple of more interesting examples. Is this okay? Okay. Suppose we have two voltages, VA and VB, connected through two diodes. That's the end of the wave shaping, and therefore we are working out a couple of examples. This is connected to ground through a 5K resistance, and this is the output V0. This is VA, let's say, and this is VB. The stipulation is, this is a given circuit, all right, two diodes, two voltage sources, one resistor, and your output is V0, all right. It is specified that VA and VB can have only one of two possible values. VAB can be either belongs to the set 0 volt or 5 volt. Alright, VA can be either 0 volt or 5 volt.
0 to 5 or 0 to 5?
No, just two discrete levels, either 0 volt or 5 volt. That means I have a 5 volt battery which I either connect or disconnect. If I disconnect, the voltage is 0. If I connect, the voltage is 5. Alright. Both of them could be plus 5 volt. Both of them could be 0. You are required to tabulate the possible combinations of VA and VB and the corresponding outputs. You see, VA, VB and V0. Suppose VA is 0, VB is also 0. Then V0 shall be equal to 0. If VA is 5 volt and VB is 0, then 5 volt. The resistance does not affect the voltage. You see, if VA is 5 volt, then this diode conducts. If this diode conducts, the drop is 0, therefore this voltage must be 5 volt. Is that okay? Similarly, if VA is 0 and VB is 5, once again this is 5 in volts. If both of them are 5, it will still be 5. What will happen to the current through 5K? Look, suppose I find the current under all these conditions. Just a minute. Suppose I find the current under all these conditions, that is the current I. Here it would be 0. Here it would be, that means 1 milliampere. Here 1 milliampere. Here No, it has to be 1 milliampere because the voltage is 5 volt.
Potential difference would
The current is still 1 milliampere, half of which is delivered from VA and half from VB. That is, basically we have two batteries now. Each battery will now give 0.5 milliampere. All right. Now, this is the rudiments of logic or digital circuit. All right. You see, if 0 volt is considered as 0 level logic, then 0 0 leads to 0, and if 5 volt is considered as 1 level in digital in terms of digital circuits, 5 volt is considered as the logic level 1, then 1 and 0 gives you 1, 0 and 1 gives you 1, and 1 and 1 gives you 1. No, this is an OR gate. This is therefore an OR gate. That is, either of the two input levels are high. Another terminology is high and low. 0 is called low and 1 is called high. So, if either of the two terminals is high, then the output is high. If both of them are high, output is high. If both of them are low, then the output is low. And the traditional symbol for this is this. There are two inputs A and B, which are basically voltages VA and VB. There are two inputs. If and the output is, let's say, C, then C is low if A and B both are low. If either A or B or both are high, then the output is high, and this is the function of the OR gate or OR logic. And this is this is a demonstration of yet another application of the diode in logic gates. A very simple logic.
So why do we need diodes here?
Why do we need diodes? All right. Suppose we don't have the diode.
In the case
Then we
when
cannot-
one of the input is low,
Pardon me?
in the case when one of the input is low, then we'll need the diode.
Yes.
We cannot do without. We cannot make a gate without a diode. Without a nonlinear unilateral circuit. That is a circuit which passes current in one direction only. You can try other combinations. You will never get an OR gate.
So what is the use of the 5K resistor?
What is the use of the 5K
So the
resistor?
current
The current has to flow.
has to be dropped.
The current has to flow because,
Otherwise it will be grounded. So
you see, suppose the 5K resistance is not there and I simply connect a 5 volt battery here. Well, what does this 5 volt battery do? It doesn't do anything. This voltage will still be 0 unless the diode is shorted. For the diode to be shorted, a current must pass. Alright? You might connect a 1 kilovolt here. Nothing will happen here till you provide a path for flow of current. Then the diode will drop 0 and you get the total voltage here. Is that okay? Let's take another example, slightly tougher. The question is, I will read the question. The output of a flow meter. A flow meter is an instrument to measure flow, that is the rate of flow or the total flow of typically, let's say, a liquid. A flow meter typically may consist of a fan-shaped mechanical gadget which when put in the path of flow, rotates. It rotates in a magnetic field and generates an EMF which is typically measured to be able to indicate the amount of flow or the rate of flow. Alright, this is called a flow meter. So a flow meter basically develops a voltage across it. Alright, a flow meter, the output of a flow meter is given by a voltage V which is equal to K times Q, where capital Q is the rate of flow, that is capital Q is, let's say, in centimeter cubed per second, cc per second. This is the rate of flow, and capital K, if V is in volts, then capital K would be in second per volt second per centimeter cube. Capital K is given as 20 millivolt second per centimeter cube. This is what is given, all right. A flow meter which is characterized by this relation, small v equal to kq, k is given like this. The effective output resistance of the flow meter has a resistance because it consists of coils rotating in a magnetic field. The coils have a resistance, and this resistance is 2000 ohms, 2K. If the flow meter is represented by a voltage generator, then the voltage generator is KQ and its internal resistance is 2000 ohms, all right. The effective output resistance of the flow meter is 2000 ohms. Design a circuit that will develop an output voltage of 10 volt. You have to design a circuit that will develop an output voltage of 10 volt when 200 cc has passed through the metering point. That is the total flow, when the total flow is 200 cc, 200 centimeter cube. Is the question clear? You have a flow meter which develops a voltage V equal to kq, q is the rate of flow, and this voltage is not simply acts like a voltage generator, it is a voltage generator with an internal resistance of 2000 ohm. What you have to do is to design a circuit, connect a circuit such that when the total flow is 200 cc, the voltage developed should be 10 volts. Now what does this mean?
So integrating it.
Integrating circuit. All right. Let us see if we can do that. What we have to do is V equal to KQ. I am not indicating a polarity right away. We shall see this. 2000 ohm. Now this resistance is already there. So why don't you use an op amp?
Yes.
Let this be grounded. We have to use a capital C here. Capital C, and this is V0.
So why do we use only the inverting terminal of the op-amp?
Why do you use? Why don't
we
we?
can use the non-inverting also, so
Yeah.
that we get the voltage in place.
There is a reason. The non-inverting terminal, anything connected from the non-inverting terminal to the output causes positive feedback. Positive feedback is like if a half insane person is on a sagging bridge and you remind him that the bridge is sagging, well, he will make sure that the bridge goes down. Is this known to you? No. Okay. Positive feedback encourages oscillations, and once oscillations start, the circuit will produce nonsense. It will not act in the manner that you like. For operation of an operational amplifier, negative feedback is a must, and therefore we make a preferential treatment of the inverting and non-inverting terminals. In most of the applications you will see the non-inverting terminal is not touched. Preferably it is connected to ground. We do all operations with the non-inverting terminal because anything will connect from the non-inverting terminal to the output causes negative feedback, and therefore it stabilizes the gain. You could not do this with the positive feedback. This is a practical point and you must remember this. Alright, now the point is that V0 is the result of an integration. You notice that in this circuit V0 is equal to minus 1 over RC 2000 multiplied by C integral V dt, alright, integral V dt. Which is equal to minus 1 over 2000 C, well V is KQ, so K integral q dt, provided our polarities are like this. Now we don't want a negative voltage, we want a positive voltage, and therefore what we do is, instead of connecting like this, we want a plus sign here. So instead of connecting the flow meter like this, we connect it in the opposite direction. Then this sign shall be, this is okay, this sign shall be positive. Is that okay?
Yes.
And integral q dt, what is given is that 10 V0 should be equal to plus 10 volts, when integral q dt, that is the total flow, is 200 centimeter cube. Therefore, all that is required to find out is the value of C, the capacitance. And if I clear this out of the fractions, we get 10 as equal to K divided by 200 C, 2000 C multiplied by 200. And K is, therefore C is, well, take this 200 out, left with 10. So C should be equal to K divided by 100, and K is 20 millivolts, that is 10 to the minus 3 centimeter per second cube divided by 100. So it is 2 times 10 to the 2 times 10 to the minus 4 farad, which is equal to 200 microfarad, and the solution is complete.
So could we use a resistance in case of a capacitance?
Could you use a resistance in place of a capacitance? Then it will not integrate. It will be simply an inverting amplifier, which is not what we want. We want a voltage to be developed when a certain amount of liquid has flown, and this voltage is required to be 10 volt. We cannot use a resistance here, no.
So for integrating and differentiating circuits,
Yes,
can we devise a circuit in which we use inductor instead of a capacitor?
quite so. We can do that. We can do that. For example, your differentiating circuit is this. All right, you can use say R and L. This is equivalent to this. This performs the function of a differentiator, and you can show this very easily. All right. Similarly, if you use series L and shunt R, this will act as an integrator. Well, this will be left to you as an exercise. Now we talk about natural response of a circuit. All right. Your behavior in the hostel is natural response. When you are not monitored by your hostel superintendent, it is your natural response. On the other hand, your behavior in exam hall is a forced response. All right, and if you are in between the exam hall and the hostel, it's a combination of both, because you're afraid that somebody is watching you. Similarly for circuits, a given circuit or a system, when excited by voltage sources and current sources, it behaves in a manner which reflects the nature of the input, and therefore that response is called a forced response. All right. For example, to a rectifying circuit, to a half-wave rectifier, if you apply a sinusoidal wave, then you get half rectified sines. All right, half of the positive, half of the sine. If you apply DC, what will happen? It will be the DC itself. All right, the rectifier or the diode will always conduct, and you shall get a DC at the output, as you saw in the OR circuit that we demonstrated. So, on the other hand, if there are no excitations, from outside, the circuit is left to itself, then it will behave in a manner which is called its natural response. Now obviously, if you have a resistive circuit, a circuit which contains only resistances, no outside interference, no outside source, all right, its response shall be identically equal to 0 everywhere in this circuit, potential or current. Why? Because this circuit cannot have any initial energy, it cannot store energy. Unless there is energy, how can there be any response? Similarly, suppose you have a inductance, capacitance, resistance circuit which has no initial energy. None of the inductors have an initial energy, none of the capacitors have a stored charge, none of the inductors have a stored flux, none of the capacitors have a stored charge. Then left to itself, it shall be completely relaxed. In other words, all currents and voltages shall be 0. On the other hand, suppose you have a capacitive resistive circuit, a CR circuit, in which the capacitor has a certain charge, all right, then left to itself, this charge shall decay in a manner which is characteristic or natural of the circuit, which is in the nature of the circuit, and therefore such a response is called a natural response. In the general situation, you might apply a voltage or current to a circuit. One of the things that you must understand is natural response, determining natural response makes sense only when the circuit has one or more energy storage elements, all right. That is, these are of two different kinds, inductor and capacitor. So natural response for a resistive circuit is identically 0. It doesn't make sense to find natural response. But if you have at least one energy storage element, then natural response means something and you have to determine the natural response, all right. In the general case, you may have a circuit which has some initial energy and then some voltage sources and current sources are applied to this circuit, and therefore the total response of this circuit shall be a combination of forced response and natural response, all right, and the sum of the two shall be the complete response of the circuit. There are two other terms which are used in this context. This is called, one of them is called the transient response and the other is called the steady state response. Steady state response of a circuit is the response that occurs after a long time has passed. That is, all the initial energies have had time to distribute or to decay. The forced response has had time to establish itself firmly, all right. Then you say it is the steady state response, and theoretically it happens at t equal to infinity. After you leave the circuit, after you excite a circuit and leave it for infinite amount of time, if you observe the response later after infinity, then you see what you see is steady state response. And what happens between the instant of application of the energy sources and the attainment of steady state is the transient response. It is like mukti or nirvana, all right. Before nirvana, before a person attains nirvana, he runs after money, he does this, he does that, he is in the rat race and so on. This is all transient response, all right. For a circuit, this is true. Till it reaches steady state, what behavior it shows is called the transient response. There is a common tendency amongst people who learn circuits at the first instance to equate natural response to transient response and steady state response to forced response. These are not necessarily the same, all right. These are four different terms: natural response, forced response, transient response and steady state response. These are four different terms. Natural response may or may not be the transient response. The steady state response may or may not be the forced response. They are not necessarily the same. Under certain conditions, they may be the same, but not in general. All right. Now, in finding natural response of a circuit, the first thing to determine is the order of the circuit. That is, how many independent energy storage elements are there in the circuit. If it is a purely resistive circuit, the number of independent energy storing elements is 0, and therefore this is called a zeroth order system. If the circuit is a differentiating circuit, for example, one capacitor, one resistor, or one inductor, one resistor, then there is only one energy storage element and it is called a first order circuit. The term order, the adjective order, has another connotation which we will come to in a minute. Now suppose a circuit has two capacitors and let's say 5 resistors. Now would the order of the circuit be necessarily equal to 2? No, because the capacitors may be trivially connected. For example, if two capacitors are in series, then you know this behaves like a single capacitor of value C1 C2 over C1 plus C2. Similarly, if there are two capacitors in parallel, then they behave as a single capacitor of value C1 plus C2. So you must be careful. The number of energy storage elements does not determine, the total number of energy storage elements in a circuit does not determine the order of the system. What determines the order of the system is the total number of, mark the word, independent. If there are two capacitors which are not trivially connected, then the circuit shall have an order 2. Alright. For example, let's take a couple of examples. Suppose we have a circuit like this. There are two capacitors, C1, C2, a resistance here, then a resistance here and a resistance here. The order of this circuit is 1 because C1 and C2 are in parallel, they behave like a single capacitor. Number of resistors does not affect the order of the system. Alright. Number of resistors do not contribute to the order of the system, it is the total number of independent energy storage elements. On the other hand, if I have a circuit like this, alright, these two capacitors C1 and C2 cannot be combined with each other in any manner because there is a resistance connected here, and therefore this order of the circuit is 2. Alright. So one thing that we learn is that the number of independent energy storage elements in a circuit, independent mind you, that is not trivially connected, determine the order of the circuit. Let's take another example. Suppose we have 3 capacitors in a loop like this, and let's say this is the circuit C1, C2, C3. Are these capacitors independent of each other? Obviously they are not trivially connected. You cannot combine C1 with C2 or C2 with C3, right? They are neither connected in series nor in parallel. They are not trivially connected, but are they independent? Can anybody answer this question? Pardon me? They are not independent. Since I am asking the question, perhaps the answer is no, isn't it? No, that cannot be the logic. You must have a logic. Say it again, say loud. What are you afraid of? That is correct. You see, KVL is true, KVL is valid, and therefore the potential difference of C1, potential difference of C3 and potential difference of C2 cannot be independently specified. So the voltage across C2, for example, if you specify VC1 and VC3, VC2 is automatically specified, and therefore they are not independent of each other. And the order of this circuit shall be 2, because only 2 capacitor voltages can be independently specified. We will go deeper into these uncomfortable questions a bit later. But for the time being, let us be happy with the identification of order of a circuit as the total number of independent energy storage elements. Now, is it necessary that all the energy storage elements should be capacitors only? No. One could have a combination of an inductor and a capacitor. Alright. You could have 2 inductors and 1 capacitor, and still the order could be 2. Is that possible? Yes, because the inductors could be trivially connected. Alright. Now, how is it that the natural response of a circuit is determined by energy storage elements and not by resistors? Well, this statement has to be taken with a pinch of salt. All right. Suppose you have a capacitor, an isolated capacitor. You charge it to a voltage of V0 and leave it undisturbed, leave it alone. Well, it will never lose charge. Its natural response will be V0. Whatever V0 you had set, it will be V0. So there is no, such things are completely boring to an engineer. If a signal, a voltage or current does not decay with time or increase with time or vary with time, it does not qualify as a signal. All right, except for power supply. Power supply is a necessary evil because you cannot operate transistor circuits and op-amp circuits without a power supply. The power supply is a constant DC. You require a DC there. But in all other cases, what we require to be able to perform a given function are voltages and currents which vary with time. Well, therefore, in order that the natural response becomes interesting to an engineer, there must be a resistance somewhere, right? A purely capacitive circuit, totally capacitive circuit, left to itself, shall conserve all the voltages that has been given to it. A totally inductive circuit shall conserve all the flux which has been generated in it. And therefore, we do require at least one resistance. Otherwise, the natural response doesn't make sense. All right. And you could have, for example, an inductor in series with a resistor. Well, this is the equivalent circuit of a practical coil. If you wind a coil around a former, this is the practical circuit. You get an inductor in series with a resistance. And suppose you have a switch here, all right, which is originally connected here, and there is a current source I0 here, originally connected here. Then if sufficient time has passed, the inductor current shall be equal to I0. All right. Then at t equal to 0, the switch is thrown open to this point, which is connected to ground. All right. At t equal to 0, this switch is thrown to the other contact. Then the current generator is disconnected, and the flux generated in the inductor due to the current I, how much flux? L times I, inductance times the current. This flux now finds an easy path through this, and therefore the flux gradually decreases, or the current in the circuit I, which at 0 minus was equal to I0, I of t shall decrease as t increases. I of t decreases as t increases, and that is the natural response. This is what is of interest to us, and we shall explore this point further on Friday.
So we say in natural response we can have a charged energy storing device. Like we can have an energy storing device in which energy is stored, but we can't have external voltage because
In battery vectors we don't have external voltages at all. No.
but we
First,
can
initially it is charged, then it's left. The sources are removed. Okay.